All right, so today we are going deep on something that's, well, it's kind of like the foundation of our clean energy future.
Yeah, you could say that.
The stuff we don't always think about, the actual raw materials, the elements that make all these green technologies possible.
Right, we're talking about things like neodymium, dysprosium,
Lithium,
cobalt.
yeah, stuff that goes into wind turbines, electric vehicles, batteries, all that.
Exactly. The unsung heroes of a sustainable tomorrow.
Totally. And to really get a handle on this whole situation, we've been deep in the weeds of a research paper.
Oh, a fascinating one. It's called Critical Materials in Global Low-Carbon Energy Scenarios. The Case for Neodymium, Dysprosium, Lithium, and Cobalt.
Catchy title.
Great.
So what we want to do today for you, dear listener, is, well, basically it's like we want to distill this whole study down.
Yeah, pull out the essential nuggets.
See if there are any potential roadblocks, like as the world's trying to go green, are we going to run out of the stuff we need to actually make it happen?
The stuff that actually makes the stuff work.
Precisely. And these researchers, they really looked at a bunch of different global energy scenarios. And then based on those scenarios, they projected like how much of these four critical materials, these elements, we're going to need all the way out to 2050.
So it's not just like, here's how much we need now. It's like, what does the future hold?
Right, exactly. So by the end of this deep dive, you'll have a much better idea of what the potential challenges are and why you should care about them.
Because this stuff matters. If we're serious about a sustainable future, this is kind of the bedrock.
Couldn't agree more. So let's talk about the scenarios, the global energy scenarios they analyzed. I mean, they didn't just, pick one and run with it.
Right. No, not at all. They looked at 6 different ones.
Takes.
Yeah, they come from pretty influential organizations. Greenpeace, for example.
Okay.
IRENA, which is the International Renewable Energy Agency. The International Energy Agency, IEA.
Gotcha. Big players.
Exactly. And these scenarios, it's like, think of them as different potential futures, right? Like different pathways for our global energy system. Some are really ambitious, some are a bit more moderate.
So a range of possibilities.
Yeah. But on top of those scenarios, they also layered in what they call sub-technology roadmaps.
Roadmaps. What's that all about?
So basically, it's like, you've got these core technologies, right? Wind turbines, batteries.
Right.
But those technologies, they can evolve in different ways.
Oh, I see.
So the roadmaps kind of lay out those different potential technological pathways.
Okay. That's pretty thorough.
They were trying to be as comprehensive as possible. They also looked at, the nitty-gritty, like how much of each material, each element goes into these technologies.
The material intensity.
Exactly. And then they compared that to our best estimates of how much of this stuff is actually in the ground, the reserves and resources.
So they really did, like, they considered the whole picture.
Yeah, they left no stone unturned.
And they even factored in the uncertainties, right? Like the stuff that's hard to predict.
Oh, absolutely. They acknowledge that there are a lot of unknowns when you're trying to peer into the future.
Yeah. Like how quickly these different clean technologies are actually going to take off in the market.
Right. That's a big one.
And then, like, even if you know a technology is going to be popular, will the amount of, say, neodymium or lithium that it needs, will that change over time?
Yeah. Could we become more efficient? Could we substitute materials? Those are open questions.
Big questions.
And then, of course, there's the fundamental question of, well, how much of this stuff is actually accessible?
Like, even if it's in the ground, can we get to it? Can we get to it sustainably, ethically?
All those things factor in. So yeah, they really tried to be comprehensive in their analysis.
All right, so I'm ready to dive into the specifics.
Let's do it.
Let's start with neodymium.
Okay, good choice.
It's in the title of the paper, so it's got to be important.
It's a big one. So neodymium, and for short, it's all about magnets.
Magnets.
Powerful magnets.
Yeah.
We're talking about NdFeB magnets.
NdFeB.
Neodymium, iron, and boron.
Got it. And these magnets, they're special.
Very special. They're incredibly strong, and they're super efficient.
And that's why they're important for green tech.
Exactly. So in wind energy, for example, these magnets are used in what are called direct drive permanent magnet generators.
Direct drive.
Yeah, it's a design that's becoming increasingly popular, especially in high-speed and medium-speed turbines. Even direct drive turbines are starting to use them.
So we're talking about like more efficient, potentially more reliable wind power.
Yeah, all thanks to neodymium.
And this research paper, this critical materials paper, they really highlighted electric vehicles too, right?
Oh yeah, electric vehicles are a major driver of demand for neodymium.
Okay, so how does that work?
So in pretty much all types of electric vehicles, whether they're fully battery powered or plug-in hybrids or even some fuel cell models, these ND-Febi magnets, they're at the heart of the electric motor.
The motor.
Yeah, they contribute a lot to the vehicle's overall efficiency and performance.
So basically, the more electric vehicles we have on the road, the more neodymium we're going to need.
That's the takeaway. And the researchers, they projected just how much we might need.
Okay, give me the numbers. What are we talking about here?
Well, based on their analysis, the maximum annual demand for neodymium could be anywhere from about 135 kilotons per year, which is, thousands of tons,
A lot.
up to 258 kilotons per year.
Okay, so a pretty wide range.
Yeah, it depends on a lot of factors. But like I said, electric vehicles, they're definitely the biggest driver here.
Yeah, that seems to be the recurring theme, in the news, policy discussions, everything.
It's the future of transportation.
Right. But you mentioned a range, and it is a pretty significant range. Why so much uncertainty?
Well, a lot of it comes down to, how much neodymium actually ends up being required in each electric vehicle motor.
Oh, I see.
Or in each type of wind turbine. That can vary depending on the specific design, the efficiency gains, all sorts of things.
So even within the same broad vision of a green energy future, there's a lot of wiggle room.
A lot of wiggle room. And that's reflected in the numbers. The study's analysis, it shows that the annual demand could actually swing from a low of around 89 kilotons all the way up to, get this, 745 kilotons.
Whoa, okay, that's a huge difference.
Yeah, it's a big deal. It really highlights how much depends on the nitty-gritty details of the technologies we end up using.
The devil's in the details. Right?
Precisely.
Okay, so we might need a lot more neodymium than we're currently producing.
That's the likely scenario, yes.
But we're not just going to, keep digging up virgin materials forever, right?
Yeah.
I mean, recycling has got to play a role here.
It does. And the researchers, they factored that in. They looked at a scenario where we achieve an 80% recycling rate for these critical materials by 2050.
80%.
Yeah.
Okay, that's pretty ambitious.
It is. But if we can hit that target, it makes a big difference. So when you consider that potential recycling, the maximum annual primary material demand, meaning the amount we still have to mine each year, it drops down to somewhere between 77 kilotons and 155 kilotons.
Okay, so recycling does help, but even then, we're still talking about a lot of new mining.
We are. It's still a substantial amount. And to put that into perspective, that primary demand range, it's a 3 to 5-fold increase over what we're currently extracting.
3 to 5 times more. That's a big ramp up for the mining industry.
No doubt. It's a challenge, no question.
So let's zoom out a bit. I mean, that's just the annual demand. What about like the total amount of neodymium we're going to need over, the next few decades?
So the cumulative demand between 2015 and 2050, it's estimated to be between 2.7 megatons and 4.7 megatons.
Megaton.
Yeah, millions of tons. And when you factor in recycling, that primary cumulative demand, it drops to between 2.0 megatons and 3.6 megatons.
Okay. And is that doable? Like, do we have enough neodymium in the ground to meet that demand?
Based on current reserve and resource estimates, yeah, it seems likely.
Okay, so at least with neodymium, we're not talking about like an imminent shortage.
Not necessarily. The bigger challenge is scaling up production in a sustainable way.
Right, and making sure those supply chains are ethical and resilient.
All crucial considerations.
Okay, so neodymium, it's a challenge, but maybe not a crisis.
That seems to be the consensus.
What about dysprosium? That's another one that's front and center in this critical materials paper.
Yeah, dysprosium, it's another rare earth element often found alongside neodymium.
Okay.
And it plays a crucial role in those high performance ND-Febi magnets we were just talking about.
The magnets of the future.
Right. So dysprosium, its main job is to help the magnet maintain its strength, especially when it gets hot.
Oh, so like a thermal safeguard.
Yeah, you could think of it that way. It keeps the magnets working properly, even under stress.
Got it. And why is that important for green tech?
Well, both wind turbines and electric vehicles, they generate heat.
Sure.
And they operate in a range of temperatures, depending on the weather, the driving conditions, all that.
So the magnets need to be able to handle that.
Exactly. They need to be reliable no matter what. And dysprosium helps make that happen.
Okay, so dysprosium it's Kind of like the unsung hero behind the unsung hero.
You could say that. It's essential for making those powerful magnets work in demanding environments.
All right, so the researchers, they looked at dysprosium demand too, right?
They did, and the trend is similar to neodymium,
Meaning,
meaning the growth of electric vehicles is a major factor.
just surprised there.
Right. So, based on their analysis, the maximum annual demand for dysprosium could be anywhere from about 17 kilotons to 52 kilotons per year.
Okay, and just like with neodymium, there's that big uncertainty range.
Oh, yeah. For the same reasons, we're still not sure exactly how much dysprosium will be needed in each electric vehicle motor or wind turbine generator.
The specifics of the technology really matter.
They do, and that's reflected in the wider range they found for dysprosium. It could be anywhere from just 2.4 kilotons per year all the way up to 90 kilotons.
Wow, okay, that's a bigger relative swing than neodymium.
It is. So, yeah, there's still a lot of uncertainty around dysprosium demand.
Okay, but what about recycling? Can that help mitigate the need for new mining, like with neodymium?
It can, but it's not a silver bullet.
Okay, what did the researchers find?
So, assuming that 80% recycling rate by 2050, the maximum annual primary material demand for dysprosium, it's projected to be between 11 kilotons and 33 kilotons.
Okay, and how does that compare to what we're currently pulling out of the ground?
That's a significant increase.
Like how significant?
We're talking about a 7-fold to a 22-fold jump.
Oh, wow. Okay, so dysprosium it's a bigger concern than neodymium, at least in terms of the increase in mining that we might need.
Yeah, it's definitely something to keep an eye on.
All right, so what about the total amount of dysprosium we'll need over the coming decades? Like the cumulative demand?
So between 2015 and 2050, it's estimated to be between 0.4 megatons and 0.9 megatons.
Okay.
And when you factor in recycling, that primary cumulative demand, it goes down to between 0.3 megatons and 0.7 megatons.
Okay. And is that within the realm of possibility given what we know about dysprosium reserves?
Well, the good news is that with those ambitious recycling efforts, we can probably avoid exceeding the average reserve estimates for dysprosium in most of the scenarios they looked at.
Okay, that's something.
But it's worth noting that in some of the more ambitious low-carbon scenarios, we might get pretty close to those limits.
So it's tight.
It's tight. It's something we need to be mindful of.
All right, so we've talked about neodymium, we've talked about dysprosium.
Two of the heavy hitters.
Let's switch gears now and talk about lithium.
Okay, the battery metal.
The battery metal, absolutely. I mean, this is the element that's driving the electric vehicle revolution.
It's essential for those lithium-ion batteries that are, well, they're everywhere now.
Everywhere.
In our phones, our laptops, and increasingly in our cars and in our homes.
Yeah, for stationary energy storage too, right?
Exactly, to help balance out the variability of renewable energy sources like solar and wind.
So lithium, it's kind of the backbone of a cleaner energy future.
You could say that. It's absolutely critical. And what's interesting is that, there are different types of lithium-ion batteries.
Oh, okay, like different flavors.
Yeah, kind of. They have different chemistries. Like you've got NMC, which is nickel, manganese, cobalt.
NMC.
And NCA, nickel, cobalt, aluminum.
And then CA.
And LFP, lithium iron phosphate.
Okay. And these all have different amounts of lithium in them.
Yeah, they do. And then there are some more experimental ones like lysate, lithium sulfur, and high-O2 lithium oxygen.
Okay, so the specific types of batteries that become dominant in the market, that's going to have a big impact on how much lithium we need overall.
A huge impact.
Okay, so what did the researchers project in terms of future demand?
Well, the range here it's really vast. It goes from a low of about 1,698 kilotons per year, all the way up to 11,511 kilotons per year.
Whoa. Okay, those are some big numbers, like way bigger than what we were talking about for neodymium and dysprosium.
Yeah, lithium it's on a whole other level.
And why such a huge range?
Well, a lot of it has to do with those sub-technology roadmaps we talked about earlier.
Yeah, right. The different pathways for battery technology.
Exactly. Like how quickly do electric vehicles get adopted? What types of batteries become dominant? Those factors have a massive influence on overall lithium demand.
And the researchers, they also considered the uncertainties in how much lithium each battery actually needs.
Right, they did. And that uncertainty, it adds another layer of complexity. So when they looked at the minimum and maximum estimates for lithium content in different battery types, the projected demand range, it became even wider.
Oh, no.
Yeah, it went from about 1,093 kilotons per year all the way up to 14,366 kilotons.
Okay, so we're talking about like a potential order of magnitude difference.
Yeah, it's a huge spread.
And it all comes down to the specifics of the technology.
It really does.
So even with the same level of ambition for a low-carbon future, lithium demand could be radically different depending on how the technology evolves.
That's the takeaway.
Okay, so we might need a lot of lithium, potentially a crazy amount of lithium,
Right.
but recycling, that's got to help, right?
It does, but even with recycling, the numbers are still pretty eye-popping.
Okay, walk me through it.
So even assuming that we hit that 80% recycling rate by 2050, the maximum annual primary lithium demand, the amount we still have to mine, it's projected to be between 938 kilotons and, get this, 6,811 kilotons per year.
Okay, I'm starting to lose track of the scale here.
It's a lot. And to put that into perspective, that means we might need to increase global lithium extraction by somewhere between 12 and 88 times.
88 times what we're currently doing.
Yeah, it's a monumental challenge.
I mean, that's almost unimaginable.
It's a huge undertaking.
Okay, so annual demand's one thing, but what about the total amount of lithium we'll need over the next few decades? Like, are we going to run out?
That's the big question. So the cumulative demand from 2015 to 2050, it's projected to be somewhere between 20.5 megatons and 141.2 megatons.
And millions of tons.
Yeah. And when you factor in recycling, the primary cumulative demand, it's still a massive 15.5 megatons to 107.8 megatons.
Okay, so what does that mean in terms of like our actual lithium reserves?
Well, here's where it gets really interesting and frankly quite worrying.
Okay, I'm all ears.
So under what they call the technological change roadmap, which assumes significant advancements in battery technology,
Yep.
and across all 6 energy scenarios they analyzed, the primary lithium demand actually exceeds the upper bound of current reserve estimates.
Wait, so we might not have enough lithium that's economically extractable with current technology?
That's what the research suggests.
That's a big deal.
It is. It means we might hit a wall even if we're really good about recycling.
Okay, so reserves are one thing, but what about resources?
Resources are like the broader estimate of what's in the ground, even if it's not currently economically viable to extract.
Right.
But even there are concerns.
Like what?
So in the most ambitious energy scenario, the one from LUT University and the Energy Watch Group, even the average resource estimates are exceeded.
Oh, wow. Okay, so lithium it's a potential showstopper.
It could be. It's a major bottleneck that we need to address if we're serious about a low-carbon future.
Yeah, this is a serious takeaway for our listeners. Like, lithium availability is not just some abstract concern. It could really impact our ability to meet those ambitious climate targets.
Absolutely.
Okay, well, on that somewhat sobering note,
Yeah.
let's move on to the final critical material they highlighted in this paper, cobalt.
Right, cobalt, another big one.
So where does cobalt fit into all of this?
Well, it's another important component in certain lithium-ion battery chemistries, particularly the NMC and NCA types, which are often used in electric vehicles.
Okay, so it's also a battery metal.
It is, but it's also used to a lesser extent in stationary storage, although the study notes that there's a growing trend towards cobalt-free batteries for those applications.
So we might be able to reduce our reliance on cobalt as battery technology advances.
Yeah, that's a possibility, and the study's projections, they reflect that potential shift.
Okay, so what kind of numbers are we talking about for cobalt demand?
So the maximum annual demand, it could be anywhere from about 715 kilotons to 4,471 kilotons per year.
Okay, another big range.
Yeah, and again, a lot of that uncertainty comes down to those sub-technology roadmaps, specifically the future mix of battery chemistries in electric vehicles.
Gotcha. So it's all about which battery technologies went out?
Exactly.
And what about those uncertainties in the specific cobalt content of batteries? Like, does that also play a role?
It does, and it leads to, well, a pretty big range in potential demand, from a low of around 364 kilotons per year to a high of 7,412 kilotons.
Okay, so cobalt it's also kind of a wild card in terms of future demand.
It is, but here's an interesting twist. The study also noted that in some of the more optimistic scenarios for cobalt demand, The non-energy sectors might actually become the dominant consumers.
Oh, really? So not just batteries.
Not necessarily. It depends on how things shake out.
Fascinating. Okay, so let's assume for a moment that we can hit that 80% recycling target by 2050.
Ambitious, but let's go with it.
How does that impact the primary cobalt demand?
So even with that level of recycling, the maximum annual primary cobalt demand is still projected to be between 337 kilotons and 2,675 kilotons per year.
Okay, and what does that mean for the mining industry?
It means we would still need a substantial increase in cobalt extraction.
How substantial are we talking?
Somewhere between a 2-fold and a 19-fold increase.
Oh, wow. So even with recycling, cobalt is still a major concern.
It is. It's a potential bottleneck that we need to be aware of.
All right, so what about the cumulative demand? Like the total amount of cobalt we'll need over the next few decades?
Well, the cumulative demand between 2015 and 2050, it's estimated to be between 18.4 megatons and 83.9 megatons.
Okay.
And the primary cumulative demand after recycling is between 9.1 megatons and 52.5 megatons.
And how does that compare to our cobalt reserves?
Well, here's another concerning finding from the study.
Hit me with it.
Under what they call the continuity roadmap, which assumes that current technology trends continue, the upper bound reserve estimates for cobalt are exceeded in all 6 energy scenarios.
Oh, no. So we might not even have enough easily accessible cobalt to meet those demands.
That's what the research suggests. And in the most ambitious scenario, the one from LUT University and the Energy Watch Group, even the average resource estimates are exceeded.
Okay, so cobalt it's also a potential red flag, just like lithium.
It is. It highlights the potential for serious supply constraints as we transition to a low-carbon economy.
Yeah, it seems like our green ambitions are really running up against the physical limits of some of these materials.
That's a key takeaway from this study. And they also looked at some of the broader implications, across all 4 materials.
Okay, what did they find?
Well, one of the big takeaways is that the more ambitious we are with our CO2 reduction targets, and the more we rely on direct electrification to achieve those targets, the higher the demand for these critical materials will be.
So basically, the greener we want to go, the more of this stuff we're going to need.
Exactly. And while neodymium might not face reserve depletion issues, dysprosium, lithium, and especially cobalt, they do.
So those are the ones to watch.
Yeah, they're the ones that could potentially create bottlenecks.
We've talked about recycling, and it seems like that can help, but the study also highlighted its limitations.
Yeah, recycling is great, but it's not an instant solution.
Why not?
Well, a lot of these technologies, like wind turbines, they have long lifespans.
Right.
So the amount of material that's actually available for recycling in the near future, it's limited.
Oh, I see.
So we're going to need a significant increase in primary extraction for all these materials, especially lithium, over the next few years.
So recycling buys us some time, but it doesn't solve the problem entirely.
Exactly. And the study also pointed out another challenge.
Okay, what's that?
Well, neodymium, dysprosium, and cobalt, they're often mined as byproducts.
Byproducts.
Yeah, like they're not the primary target of the mining operation.
Oh, I see.
So their extraction rates they're kind of tied to the demand for other metals.
So we can't just like ramp up neodymium production on demand, even if we want to.
It's not that simple. It's a more complex system.
Okay, that's an important nuance to consider. So this study it's given us a lot to think about, but the researchers, they also acknowledge that, their findings aren't the be-all and end-all.
Right. They compared their work to other studies that have looked at this issue.
And what did they find?
Well, they found that the results can vary quite a bit depending on, a bunch of factors like the scope of the technologies they considered, how they estimated demand, the assumptions they made about battery capacity, and of course, the assumed recycling rates.
So there's still a lot of uncertainty in these projections.
There is. It's a complex issue and there's no single right answer.
Yeah, it seems like every study brings its own set of assumptions and limitations.
Exactly. But that doesn't mean these studies aren't valuable. They help us understand the potential challenges and start thinking about solutions.
Right. So what are some of the key differences they found between their study and others?
Well, for example, some studies might focus only on the transport sector, while this study looked at power generation and storage as well.
So a broader scope.
Yeah. And differences in the assumed battery capacities for electric vehicles, that can also lead to big variations in lithium and cobalt demand projections.
Sure. I mean, if you assume everyone's going to have a huge battery in their car,
Mm.
you're going to get a very different number than if you assume people are going to be more moderate in their battery choices.
Exactly. And even the way they combine those technology and sub-technology roadmaps, that can have an impact on the overall material demand.
Okay, how so?
So, for example, imagine a scenario where wind power relies heavily on a technological change roadmap, maybe using less neodymium and dysprosium per turbine.
Okay.
But then you combine that with a scenario where electric motors follow a continuity roadmap, relying on current magnet technology.
Okay, so one sector is getting more efficient while the other is staying the same.
Right. And that could lead to different overall demand figures than if both sectors followed the same path.
So it's not just about individual technologies, it's
Hmm.
about how they interact.
Exactly.
The study also made some simplifying assumptions, right? Like that 80% recycling rate by 2050 and a linear relationship between non-energy sector demand and GDP.
They did. And they acknowledged that, the reality could be more complex.
Like how so?
Well, for example, the demand for batteries in non-energy sectors like consumer electronics, it might grow faster than overall economic growth.